This video is a description of the reactions of aldehydes and ketones for the survey of chemistry. The reactions that we are going to explore are the oxidation of carbon, the reduction of the carbonyl, and the addition of alcohols to ketones and aldehydes. The reaction of oxidation can take place in different fashion. The first type is when we have a carbon-oxygen, like in the family of alcohols, that will be transformed into a carbon-oxygen double bond. In the same reaction, we will need to have a hydrogen to be removed with the oxidant as a molecule of water. The second type of reaction is when we increase the number of oxygen in the final product, like in the family of aldehydes, with the transformation into a carboxylic acid. In the chapter of alcohols, we observe how a primary alcohol, that is, an alcohol where the carbon that bears the OH is bonded to one carbon or more carbons, produces an aldehyde. For example, the reaction between the mild oxidant PCC and the primary alcohol ethanol will produce the aldehyde named ethanal. Hydrogens bonded to the carbon that bears the OH has combined with the oxidant to be removed as molecule of water. As we have discussed, if the primary alcohol is reacted with a strong oxidant, the intermediate aldehyde is not isolated, but it will be transformed into a carboxylic acid. We also discussed how a secondary alcohol can get oxidized to produce a ketone. However, the ketone product will not undergo further oxidation. There are no hydrogens to be removed. An addition of oxygen will produce a carbon with 5 bonds. We can summarize the reaction of oxidation of these carbonyl compounds as aldehydes will oxidize to carboxylic acids and ketones will not undergo oxidation. When exploring these reactions, it is important to recognize what are reactants and reagents. In the reagents list of oxidants, we can look at potassium dichromate, potassium permanganate, the Benedict reagent, which is very important for the study of carbohydrates, the Tollens reagents that will produce a silver mirror deposited in the inside of the glassware. Aldehydes are so sensitive to oxidation that even atmospheric oxygen will transform them into carboxylic acids. To protect these substances, the aldehydes are sealed in a container under an atmosphere of nitrogen. In this example, we observe the transformation of benzaldehyde into benzoic acid. Observe that the carbonyl is not part of the aromatic benzene ring, and it has been transformed into a carboxylic acid group. Regardless what molecule is given to you in any exam or quiz, only explore the functional group. The rest of the carbons, the rest of the molecule is not being changed. The oxidation is only going to take place on the carbonyl. So we see here the benzene aromatic ring remains. There is only a change in the functional group. The second reaction that we need to explore for the family of aldehydes and ketones is the reaction of reduction of the carbonyl to form alcohols. We have seen the reaction of reduction of the carbon-carbon double bond in the family of alkenes to produce alkanes. Since this is an addition reaction, the first step will be to break a double bond and then rewrite the frame of the molecule, add 2 new bonds, and then add 2 hydrogens. In the family of aldehydes and ketones, we'll proceed in similar fashion by breaking the double bond, rewrite the frame of the molecule, and add 1 hydrogen to the carbon to give an octet, and also 1 hydrogen to the oxygen. Reduction of aldehydes yields primary alcohols, and reduction of ketones yields secondary alcohols. For the reduction of alkenes, we always used hydrogen gas in the presence of a catalyst. However, in the family of aldehydes and ketones, we will be using what is called hydride, and that is a hydrogen with 2 electrons. A good source of hydride is sodium boron hydride. It is important to understand that a hydride does not work for the reduction of an alkene carbon-carbon double bond, while it does work very well for the reduction of a carbon-oxygen double bond. When we explore the carbonyl, the first thing that we see is that oxygen is more electronegative than carbon. We have 2 lone pairs that will make oxygen with the partial negative charge and carbon with the partial positive charge. Because the hydride ion carries 2 electrons, it will be attracted to the partial positive charge of the carbonyl carbon. This hydride will add to the carbonyl, breaking the carbon-oxygen double bond. If this carbon-oxygen double bond does not break, upon addition of the hydride, it would have 5 bonds. If we explain the mechanism, it will require the addition of a hydride to the carbonyl, opening of the bond between carbon and oxygen, and the catalyst will bring a second hydrogen. As the result, the reaction between sodium boron hydride and an aldehyde will produce a primary alcohol, and if it is the use of a ketone, the product will be a secondary alcohol. In this example, we use the molecule of ethanol that in the presence of hydrogen gas, using nickel as a catalyst, will produce ethanol. If the reaction is between the hydrogen gas and a ketone, like 2-pentanone, the product of the reduction will be a secondary alcohol. I have written the molecule twice just to remind you that this is a secondary alcohol because the carbon that bears the OH is bonded to 2 carbons. Also important to check that we still have 1 hydrogen here. So 2 hydrogens were added, 1 to the oxygen and 1 to the carbon. Also observe that it does not matter what is the size of the aldehyde, only the functional group is undergoing a transformation. This carbon, number 1, it was butanol and it has become 1-butanol. Let's look at the reduction of 3-pentene 2-on, which is a ketone in carbon number 2 and an alkene on carbon number 3. In this reduction, if we use an excess of hydrogen in the presence of a catalyst, we will obtain an alcohol, and both of the unsaturations will be destroyed. If instead we use hydride, like sodium boron hydride, only the carbonyl carbon-oxygen double bond will be destroyed, and the product is 3-pentene 2-ol.